Okay, so far 14, 15, 14 of you. $16, okay. Hold on, yeah. Okay. Right, let me share the content. Okay, can you see the slides? Okay, all right. Alamak, ada lagi. Yep, yeah. Some of you still joining. Mm, 19, okay, all right. Okay, let's get started. So today we're gonna continue on with the first topic of this course, which is on introduction to semiconductor fabrication. So this is again is gonna be a brief overview of this course. Okay, so we're gonna start off with this. Um, so this is an example of a wafer being used in integrated circuit fabrication. So can you guess what's the diameter of the two wafers? From the image, can you guess what's the diameter? Any magic number for the left, for the right one? Anyone knows what's the diameter of the two wafers? No idea. So the big one is 18 inch. 18 inch is 450 mm or 45 cm, and left one is I think 8 inch or no 10 inch I think. Yep. Right. Okay, slightly smaller. So what makes integrated circuit? We've learned last time. So silicon makes the integrated circuit. Okay, and silicon's origin is from silicon dioxide, which is basically sand or SiO2. So to be able to get the silicon with the right level of purity, we need to first remove the oxygen from the silicon dioxide to make it silicon, and then we need to purify silicon up to certain purity level before it can be used for fabrication. Okay, you still remember what's the purity level of the silicon required for integrated circuit? How many Ns? How many Ns have to be in the silicon for it to be used in fabrication? Right, any guess? Kita dah belajar tu kan, from 386. Berapa N? How many N for a transistor to work? Yeah, 9N. 9 or 10, Izian? 9N, eh? So what does it mean by 9N? 99 point? 1, 2, 3, 4, 5, 6, 7. Okay? So 99.7 more of 9s. So for it to be used as a transistor or integrated circuit, it has to have a purity level of 9N. Right? Baru kita boleh fabricate and a functional transistor. Okay, so this is the most the highest level of purity required for the device. Are your friends joining now? Let me go back to the. Okay. Okay, so it's 9N for integrated circuit. So how many N's do we need for solar cells? Anyone? Berapa N for solar cell? We've covered this one as well last time when we discussed in 386. Berapa purity for solar cell? Silicon solar cell. Anybody? Just tengok nama. Tak ada dalam kelas, susah sikit yang kena tengok nama. Alrighty, I've got the name. Hazika. Hazika? Can you hear me?
Yes, Doctor.
Ya, khabar sihat?
Sihat, Alhamdulillah.
Okay. Berapa N for solar cell? Silicon.
Solar cell, 90, I think 98.
98%?
Yes.
Okay, and right. Okay, thank you. Any other guess? Kalau kita duduk dalam dewan kuliah senang sikit, saya tunjuk-tunjuk. Sekarang susah sikit online ni. Naim. Can you hear me, Naim? Naim? Naim tak jawab Jenny.
Hi, sir.
Hi, how are you?
I'm good.
Right. Okay, how many N's do you think?
93.
93?
Yeah.
90% purity.
Yeah, I think so.
Okay. So ada orang lain nak tukar. Okay, last one lah. I give a chance to Inas. Inas? Lama tak dengar suara ni, semua dah duduk online kelas kan? Inas, are you there? Right. Okay, Inas. How many N's for silicon solar cell do you think? Integrated circuit, we need 9N. So, integrated circuit, kita perlukan 9N. So, how about silicon solar cells? What do you think? Does it have to be at the same level? 96%. Okay, 96%. So, we got 96%, 93%, 98%, right? So the answer is, if you want to fabricate a functional silicon solar cell, how many n's, right? So it has to have 6n. Okay, 6n. Apa maksudnya? 99.1234. Okay, silicon solar cell 6n. 99.9999. 6 kali 9 lah. So lower than that, it will not be functioning, right? So if you compare the purity level of integrated circuit and solar cell, which one is higher? Which one is higher? Straightforward again. Yeah, I think one of your friends joining now. Hold on. Oh, okay, all right. Okay, hold on, yeah, no problem. Okay, so if you compare 9n versus 6n, mana lagi tinggi? Of course 9n lah kan. So what does it mean? Right? Good. 9n is higher, right, Farah? So that means in order for you to have a functional integrated circuit, you have to have a very good purity of silicon. And on the other hand as well, it also means that silicon solar cell is more defect tolerant if you compare to integrated circuit. Sebab maksudnya kalau dia ada 6n purity pun dia dah okay, tapi kalau you pakai integrated circuit 6n is still not okay. So integrated circuit still requires 9n. Maknanya kalau you use 6n silicon for integrated circuit, it won't be working. But it will work as a solar cell, but not as an integrated circuit. So because of 9n requirement and 6n requirement, right? So that's what it means. So we have to remove the oxygen from the silicon dioxide or from the sand, and then we need to purify the silicon once the oxygen is removed until it reaches 9n purity for silicon. Then only you can use it for integrated circuit fabrication. Okay. Nanti we're gonna go to the specific process for it to be 9n. So silicon chunks are processed to become bare silicon wafer. So after you've done a couple of processes, we're gonna cover this one later when we talk about crystal growth and conversion from sand to polycrystalline to monocrystalline. So eventually, after the growth process, you're gonna get polysilicon chunks. Polysilicon chunks ni yang belah kiri tu, yang kumpulan silicon tu. So it's called polysilicon chunks. Macam batu. So at this point, the chunk already have some level of purity. We're gonna cover that later on. Then eventually we want to convert those silicon chunks into bare silicon wafer yang flat, right? So the thickness is typically 500, 600, depending on the type of industry and devices as well. So if you talk about integrated circuit, it's typically 400, 500 micron thickness. So that's about 5 times our hair thickness, right? If you assume our hair thickness is 100 micron. So the moment you have your bare silicon wafer, then only you can do the integrated circuit fabrication on the bare wafer. Okay, a little bit of history of transistor. So germanium was one of the first few materials used in the device fabrication. So the first transistor was in fact made of germanium back in 1947 in Bell Labs in the US by these 3 scientists, Bardeen, Bertin, and Shockley. And it was then replaced by silicon in 1960s. So why silicon? Why silicon replaced germanium? There are a few reasons for that, but it's not the whole reason. It's only part of the main reasons. Silicon can be oxidized easily for high quality SiO2. So we'll discuss about SiO2 last time. Still remember what's the role of SiO2? When you talk about MOSFET. So what? Still remember what's the role of SiO2 in MOSFET device? The last part of your 386 last time. Nabila, can you hear me? Nabila, ada? Ada? Syah. Nabila, okay, Nabila. Ya, gate oxide. Naim tolong jawab orang. Saya tanya lagi. Right, the role is as the gate oxide, right? So, it's a very thin layer of between the gate and the silicon, right? So, gate oxide. Role is as gate oxide. So, in order to form gate oxide, we're gonna learn later on. We need to oxidize the silicon to form the desired thickness in order to form the gate ox, right, or effective barrier in diffusion process. Then the second reason, silicon has higher band gap compared to germanium. So ingat lagi tak silicon band gap versus germanium punya band gap? What's the magic number for silicon? Berapa silicon? Nabila pula lah. Nabila, what's the band gap of silicon? Anyone? Okay, 1.1, right? 1.12. Okay, close. Thank you, Ilham. So 1.12 electron volts. So what's the band gap for germanium? So on the lower side. Yeah, germanium is 0.7, close. Thank you, Farah. So it's 1.1 versus 0.7. So higher band gap means the material or the device can operate at higher temperature. Why is it so? Kenapa higher band gap device or higher band gap material can operate at a higher temperature? Can you relate with 386 last time? Can you relate with thermal excitation? Jadi kalau we operate at higher temperature? Still remember the Fermi-Dirac distribution function at 0 degrees T1, T2? Apa jadi? As we go to higher temperature, so what's going to happen to the valence band? Valence band electrons, they're going to be excited into conduction band, right? So the higher the temperature we go, the more valence band electrons get excited into the conduction band for conduction process. So maksudnya, if you use higher band gap material, so you're going to end up with a more stable device. It's not going to be affected by thermal excitation at high temperature, right? On the other hand, if you use material with lower band gap, so it's easily affected by the thermal excitation, even though you increase the temperature slightly, right? So higher band gap device is therefore more thermally stable. Okay. Then the third reason is silicon is abundant in nature, right? SiO2, sand is abundant in the earth crust and therefore inexpensive. Okay. Right, another popular material is gallium arsenide, or gas. Is usually used for high electron mobility transistors due to higher electron mobility if you compare to silicon at any particular doping level. If you go back to the content in 386, if you can recall the mobility against the doping level of different materials, for example, silicon, gallium arsenide, or germanium, either they are p-type or n-type, we can see that the average electron mobility for gallium arsenide, for example, if you choose 1018, 1e18 centimeter minus centimeter cube minus 3 centimeter, yeah, centimeter cube per centimeter cube, the electron mobility will be higher for gallium arsenide in comparison to silicon. So that's why we use gallium arsenide for a higher electron mobility transistor, or higher switching or faster switching device. Okay, so it's usually more favorable than silicon. So this is again the invention of transistor back in 1947. Look at that shape of the germanium transistor in Bell Lab. You can see here clearer this page, right? How does it look? It's not looking good, right? But it's working. 1947. That's like what, 60, 80, 70 years ago. Simple shape germanium BJT. The first integrated circuit was fabricated back in 1958. So when we say it's integrated circuit, so that means the circuit consists of more than one component, right? That's why we say it's integrated, right? So it doesn't look well, but it's functioning as the first integrated circuit. So this circuit consists of, you can see from the centers there, resistors, capacitors, transistors. So there are more than one component on the device. So that's why we call it integrated circuit. 1958. And this one is the evolution of the integrated circuit since back then, right? 1971. So the processor from Intel 2004, the frequency of the operation is only up to 108 kilohertz. So sekarang punya laptop berapa dia punya processor? Berapa processor? Do you know the processor of your laptop? Berapa sekarang? Are we still in kilohertz? No, right? Sekarang dah gigahertz, right? Okay, Farah. Sekarang kita dah gigahertz. So gigahertz is 10 to the 9, right? So this one is only 10 to the 3. So 1 million of magnitude higher. So PMOS, the processor composed of PMOS, only 10 micron process. So that's very, very thick. So big transistor. So then Pentium 4 in 2000, 42 million transistors, 2 gigahertz operation, 0.18 micron process. Okay. Intel 2 quad, 2.83 gigahertz, 45 nanometer, right? 820 million transistors. And the latest one, or among the latest one actually, is the Kirin Huawei 7 nanometer process by TSMC, 10.3 billion transistors in 200 squared area, right? This is in this year. So today we can see in a typical integrated circuit, usually they consist of billions of transistors, right? Just as what you see here. So you can see different chips there, thousands or at least hundreds of thousands of chips on the wafer, right? Inside is the detail of every chip is just like what we saw yesterday on the YouTube, right? So back in 1965, there's an observation made by Gordon Moore. Gordon is one of the co-founders of Intel. So, and this observation is called as Moore's law. So, it's called a Moore's law, but then it's not it's not a law, but rather an observation made by Gordon Moore. So he noticed that back then, he noticed that number of transistors per square inch on integrated circuits usually double every 2 years since the invention. So that means every 2 years you will see doubling of transistor pack onto the same area of the chip, right? And Gordon Moore predicts that this trend will continue into the future. So until now, we can see that the number has really gone down to close to the limit already. Not just yet, but already close. So we're now down to around 5 nanometer, right? Because we want to do smaller transistors. And when we talk about smaller transistors, that means faster, you can fit more and consume less of electricity for the operation. Okay, so what does it mean by the the smaller transistor? So if you look at the figure on the left hand side, right? Figure on the left hand side. So that shows the width of the gate in micron against year. So currently we are 2020. So you can see the trend there. So it has gone down from what 1 point something micron, right? 1 point something micron there. Oh no, 2 or 3 micron is log scale, down to around 14 nano if you talk about 2014 maybe, somewhere there. So it's gone down. So what this means is actually the micron on the y-axis means the gate length, right? The gate length. You can see on the right hand side. You can see on the right hand side. So this is the gate length. So that means back then in 1970s, the gate length was somewhere around 5 micron maybe. The capability of the process that we can do. So now we have gone down to 5 nanometer as of 2020. In fact, we are going closer to 3 nanometer, right, by TSMC. So there's the gate length. So you can see the original paper later on. So the link is there already. So this is Gordon Moore with the wafer with integrated circuits printed. So this is also Moore's law. You can see the number of transistors on the y-axis against a year of introduction on the x-axis with different technology name since 1971 till 2016. So you can see the number of transistors increases tremendously over the course of 40-50 years. So this is a summary, simple summary up to 2008. If you like, back then 1971 is only 2,300 transistor, right? So now it's million and in fact billions over this over the same area. Okay, so this is the same thing as well, but instead of number of transistor, so it shows transistor size or the gate length to be more specific. So that means in 1971 the gate length is somewhere around 10 micron, and now we are now more than this. We are now down to 5 nanometer, right? So about 10 years ago we're down to 45 nanometer. So this is the clock speed, the very same thing, but in different parameters. Clock speed, we are now up to almost 3 gigahertz, right? So you can see the summary table here by ITRS. So if you want to see what's going to happen in the future, you can always refer to International Technology Roadmap for Semiconductors or ITRS. So this is a template formulated by scientists, researchers, industries worldwide on how semiconductor is going into the future. Wafer size also increases time. Back then it was only 100 nanometer, 100 mm in size, in diameter. So in the 1990s, most of the fabs were using 200 mm or 8-inch, right? Then some fabs to 300 mm, and some even go to 450 mm, right? So Silterra is here, 8-inch, Silterra 8-inch, 200 mm. So sorry. So some giant fabs are doing 12-inch, 300 mm, right? 300 mm. So Silterra is doing Silterra is doing 8-inch or 200 mm. So what does it mean if you go bigger? Apa maksudnya if you go bigger? If you go to bigger wafers for the fabrication process, so that means you can pack more transistors onto the same wafer size, but it also means that you need to change the production line. You need to change the size of the equipment, the size of the wafers in order to accommodate bigger wafers. So that means kalau you tengok wafer fab di Malaysia, in fact worldwide, wafer fab ni is created or is constructed in such a way that you know that this production line is going to run 8-inch or 12-inch or 18-inch. You cannot mix between 8-inch, 12-inch, and 18-inch punya production line because the chamber for each process is going to be different. So maksudnya kalau you run from process number 1 until process number 200 for 8-inch, the whole line has to be 8-inch. If you want to do it for 12-inch, then the whole line has to be 12-inch. So you cannot be lithography running 8-inch, etching running 12-inch. No, it's not going to work, right? Because you need to retrofit or you need to change the equipment that you use for processing. And it's also worth to take note that if you go for bigger wafers, the cost for constructing wafer fab is going to be higher as well because everything is going to be scaled up, right? My production line you can scale up because the chamber pun dah besar, so your equipment space will be bigger. Equipment space will be bigger, then the chamber will be bigger, then other things will be bigger as well in order to accommodate the wafer size. Okay, so next. All right, back in 2017, so IBM figures out how to make 500 chips. This is usually realized by EUV process, extreme UV process. We're going to learn what is this later on. So the wavelength is 10 to 14 nanometer, right? So you're going to see how this exposure wavelength of the system evolve as well when we discuss about photolithography process later on. Oops, sorry. Right, 5 nanometer chips can only be fabricated if you have extreme UV system or EUV system. This is mainly on the lithography process. So lithography is the heart of the fabrication. So because it's gonna do all the printing process. So that means kalau you're capable to print that small, then other processes in the fabrication have to follow lithography. Etching, implant, diffusion have to follow lithography according. But if your other processes can do minimum size or lower size, but your lithography cannot, no point. So maksudnya you tak boleh print smaller anyway, right? And to be able to print small size, so small size means here if you're talking about sub 10 nanometer, or in fact if you go for 22 nanometer and below, you dah kena ada EUV system, EUV lithography system. So the size is very big. So you can see from the image here. I think the size is hard to show now. Kalau you ingat size BT, what BT only the size of one piece of lithography equipment for EUV. So lebih kurang 1 BT tu lah, dia punya size. So in a typical production line, if you talk about Silterra, when I left last time, 2009, lithography production line has about 18 equipments. So kalau you imagine 1 BT tu is 1, then you need to have 18 of them in one production line for photolithography process only. Tu tak termasuk other processes lagi ya. Diffusion, implant, lithography, etching, thin film deposition, CMP. So that's why the fab itself is usually very, very big, right? So down here is the inside of EUV, just an introduction to you. So ASML is a company based in Netherlands, in Eindhoven. So they are the one who manufactures this EUV scanner. Scanner, kita panggil dia scanner. Kita akan belajar later on dalam lithography, don't worry yet. So proses dia macam scan, you scan kertas dekat 3-in-1 printer tu kan. So it's scanning the thing, but instead of scanning the paper, you are scanning the circuit, and then you want that circuit to be imprinted onto bare wafer, and you get the patterns there, right? So that's the basic. All right, this is TSMC, Taiwan Semiconductor Manufacturing Corporation. So they've just celebrated. So if you look at the date there, it's August. So it's August, right? August 2020. So it's just 1 year of TSMC celebrating 1 billion of 7nm chip production. So that means they've just reached a milestone of production for their 7nm chips since last year. So they are now the first in the world for the what we call high performance, right? So in fact, this is their target. So saya baru snap daripada TSMC website. You can see here their future R&D plans. If you wanna see where they're going with the future technologies. So if you look at the first row there, 3nm logic technology platform using 3D CMOS, FinFET or GAA FET, gate all around or FinFET technology. So they are basically categorized as 3dimensional CMOS, even though they are not only CMOS, right? So projected for risk production in 2021. So just next year, 3nm is coming by TSMC. Beyond 3nm logic platform, 3D for SoC, silicon on chip, risk production is targeted in 2023. 3D IC, system in package SIP, I think now is ongoing based on the schedule there. Next generation lithography covering EUV and related patterning technology to extend Moore's law. So that means they want to prove that we can still push Moore's law to the limit, right? Okay, 2018 to 2021, and in fact, their long-term research as well is included here. Or SoC technology, including new non-volatile memory, NVM, MEMS, micro-electromechanical, right? Micro-electromechanical MEMS, RF technology, analog transistor for the future production. So this is already clear by TSMC roadmap. Okay. So Moore's law will not stay forever. Why is it so? Because it will reach fundamental limit. Why do you think Moore's law will not stay on forever? Sekarang kita dah dekat 5nm production. So TSMC is pushing for 3nm. How low can we go? We'll reach fundamental limit means what? What does it mean? What do you think it means? Faika, any idea, Faika? What will be our limit? Size of atom. Good. Yes, size of atom. So if you talk about size of atom, so we're talking about silicon, then what is the size of silicon atom? Cuba Google sekarang, what's the size of silicon atom? I give you like 10 seconds. Anyone can share? Size silicon atom. If the limit is size of atom, so that means we are limited by size of silicon. Kalau tidak, kita kena potong silicon lah. So, siapa dah dapat? Google answer. What is the size of silicon atom? Anyone? Siapa dapat, tulis je kat situ. Cuba Google je. Size of silicon atom. You'll find the answer right away. 200 picometer. How big is 200 picometer? So now let us translate into nanometer. Sebab kita tengah cakap tentang nanometer kan. So we are now fabricating 5 nanometer chips through TSMC. So then we'll reach the fundamental limit. Yes, good. 0.2 nanometer. So maksudnya sekarang ni kita ada 5 nanometer. So the fundamental limit will be 0.2 nanometer, or else maknanya silicon atom tu 0.2 in diameter. Besar dia 0.2 kan, I don't have a ball. Okay, so kalau you nak go beyond 0.2, that means you have to cut the silicon atom kan. So that means that's another mechanism already, right? So we are now 5 nanometer, so the limit is 0.2 nanometer. So the question is, we can go down to the limit. It's just that, can our printer or lithography process print down to 0.2 nanometer? So the answer for now, for 2020, is no. So nanti kita akan belajar dalam lithography process. You will see that lithography process is actually driven by optics. Dia akan ada objective lens, there'll be focusing, there'll be many objective, there'll be many optics lah, optics punya configuration dalam tu. In fact, you can see from the previous image of SML punya scanner pun, they are, we call it projection optics. So there's a limit for the projection optics on how small can it go, right? So that means you have to really focus the light down to 0.2 nanometer to be able to fabricate 0.2 nanometer chips, functional without issues related to quantum mechanics, right? Bila kita dah pergi ke quantum level, dia akan ada, we've learned last time, right? Quantum tunneling, all the stuff. Some other new, we call new mechanism will be in the picture, right? That we didn't see at the bulk level. Okay, so it cannot go on forever, but then to be able to go down to, in fact, 3 nanometer is already hard enough and expensive enough. So to be able to really focus the light down to 3 nanometer, just like what TSMC is doing, is already difficult and expensive enough. So let alone 0.2 nanometer. Okay. So in terms of size of transistor, you can see that we are approaching the size of atoms or silicon atoms, to be more specific, as a fundamental barrier, which will be 2 or 3 generations. Before we get that far, I'm not sure how fast can we go, and of course it needs money to go faster. Later on, we'll see how much investment is needed for you to buy an EUV system, right? So you can see the direction of Moore's law and what is the opinion on Moore's law and what Intel's take on that, right? And on Moore's law, a start of a new golden era. 2019 article, you can see what's the point there. All right, a little bit more. Malaysia's EE value chain. So we have been talking a lot about TSMC. So to put that in perspective, kita tengah discuss TSMC because it is a wafer fab, right? If you talk about EE value chain worldwide, and to be more specific in Malaysia, so we need firstly a design house. You need to design your IC first. Integrated circuit you nak print tu, you have to firstly design them on the circuit level, barulah kita boleh print, right? So this design in the wafer fab will be called reticle. Nanti kita akan tengok dalam lithography process. Reticle ni macam mask lah. Mask yang pattern of circuit yang you akan print on the silicon using the light in lithography process. So the circuit has to be designed first, then only you can use your circuit in wafer fab and to do all the fabrication process. So the moment wafer fab is done, so we're going to end up with wafer yang banyak, yang penuh dengan chips, so right? So then we're going to send to assembly and test. So this is this is the front end wafer fab ni. Sini back end. Back end is assembly and test. What they're gonna do is they're gonna take the completed wafer and then they're gonna do the dicing process. They're gonna cut the chip into one specific chip from the wafer, and then they're gonna test each of the chips, and then they're gonna do the packaging. Then it's gonna end up on board or eventually in the products, right? So that's how it looks like. And the focus for this course is mainly on fab and a little bit on packaging later on. So we're going to cover this, right? Our focus. So the process, just a brief run through before we actually go to respective process. So we're going to start with polysilicon chunks after we've done the purification process. So then we're going to do crystal pulling or crystal growth. We call it Czochralski process. So we're going to melt CZAT process, Czochralski, where we're going to melt the polysilicon chunks in a big chamber at high temperature, exceeding 1,400 degrees C, because so that's the melting point of silicon. Silicon will be melted, and then you're going to inject boron or phosphorus as the dopant to make sure that your ingot here is either p-type or n-type, or you can in fact choose not to dope the ingot to make it intrinsic. So we've learned about p-type, n-type, intrinsic. So your ingot can then be either p-type or n-type or intrinsic as well. So then we've got the ingot, macam bantal tu. Then we have to do the cutting to cut the ingot. So you have to cut them into wafers, right? So depending on how big is your how big and how long is your ingot. So this ingot, if you talk about 8-inch, then the ingot will be 8-inch. If you talk about 12-inch, then the ingot will be 12-inch in diameter. So then the wafer will be getting the exact same diameter from the ingot. Then after you have done the cutting, then it's going to end up as one specific wafer in the cassette, and then we can now do the fabrication process. Okay, then, yep, this is among the fabrication process. So this is the Czochralski process. We're gonna go to the details later on. This is just a brief. So we're gonna melt the silicon chunks here. So they're gonna be melted, and then we're gonna do ingot pulling process. So you can see here. So that's the line there is actually the seed. Kalau you nak grow silicon 100, then the seed there yang masuk dalam melt is going to be 100 oriented. Then you're going to do a slow pulling process at some rotation of the ingot, and then you're going to end up with the orientation of the ingot following the exact orientation of the seed. So kalau you pakai seed 100, then the whole ingot there, the whole ingot here will be 100. Kalau pakai seed ni 1-on-1, then you're going to end up with seed 1-on-1. So depending on what do we want. So we need to do a slow pull process to get the whole ingot, and then the ingot will be cut and then sliced to get the wafers, right? Okay, basic fabrication processes that we're going to learn later on. It's called device fabrication process. Processes involve oxidation, lithography, etching, diffusion, implant, thin film deposition, metallization. So you can see here briefly. So the moment you have cut your ingot into wafer, so the wafer is going to be clean. So you're gonna start off with a clean bare wafer, and then we're going to grow oxide using oxidation process, a very thin oxide, and this oxide is usually used for gate oxide or pad oxide, depending on the device architecture. right? Then we need to apply photoresist. Photoresist ni dalam lithography process, it's a light sensitive polymer. So that means they can react based on the wavelength of the light. So that's one of the reasons why the lithography space has to be yellow in color, right? To avoid contact with visible light that will induce some other mechanism in the photoresist. We're going to learn later on. Then you're going to do the alignment in the EUV or other UV system, or basically we call it scanner system, where the printing by light will take place. Then you're going to do exposure, same thing in the scanner system. Then you're going to etch the oxide. So nanti kita akan tengok kenapa you end up, why do you end up like this? Why not remove here and here maintain? So we're gonna see what's actually going on. So this is just a brief, don't worry yet. Then the moment you have got this structure, katalah you ada ni, you ada oxide on the left, oxide on the right, and the central area is open, you can actually dope the central area because it's open. So area yang belah kiri dan belah kanan tu will be actually blocked, will be masked, will act as a mask to the dopant. Maksudnya dopant boleh masuk kat tengah. So you can actually design where your dopant will go into the silicon based on the previous lithography and etching process that we'll see later on, right? So yeah, that is the introduction. Yeah, I think that's all for the introduction. So can you follow so far at this introductory phase? We're not into any process yet. This is just a brief overview to explain to you on where wafer fab is in the ecosystem. So what processes involved, where are we going in terms of technology. Nanti you boleh explore yourself, where are we going, why TSMC is going this way, why not the other way. And in fact, TSMC is not the only one. We also have, if you talk about top fabs in the world, you have GF, Global Foundry, we have TSMC, we have SMIC, we have UMIC, we have what else? Top fab. We have Samsung, we have Intel. So these are all top guns, top 5, top 10 in the world. So what we have in Malaysia is not a top one, but it's among the most complicated technology that we have in the country. But when you say is the top one, they are usually driving technology to below 22 nanometer or below this, right? Below 22. So remember last on Monday, right? On Monday I showed you on the slide that if you put Silterra as a comparison, then Silterra can only do down to 100 nanometer. Ini je kita boleh buat. So if you want to go beyond 100 nanometer, you have to buy another equipment, right? And that's like super expensive, right? So you can follow, yeah. Okay. Okay, that's good. For the next one tomorrow. Tomorrow is Thursday, right? Thursday. Right. Thursday we're gonna cover crystal growth. So we're gonna look at the conversion of sand to polysilicon, and then followed by conversion of polysilicon to monocrystalline silicon, right? So the one that you see on the wafer there is actually monocrystalline. We cannot use polycrystalline wafers for integrated circuit fabrication. Only monocrystalline can be used because we don't want to have grain recombination. That's what we learned last time in 386. Right, any questions? Almost 3. Anything? All good? Ada? All right, then. If no question, then that's it for today. Then I'll see you tomorrow, 2 p.m. Inshallah. Okay. Bye-bye. Salam. Take care.